You're here for the 52nd Celebration of Mind virtual presentation with Karl Schaffer. Karl's going to be presenting to us Kinesthetic Conundrums. My name is Rhody. I am hosting, and Karl Schaffer is a dancer slash choreographer and a mathematician who takes a playful point of view about both disciplines. Karl enjoys exploring the sometimes surprising connections between them. His recent concerts include Nevertheless She Persisted, the Daughters of Hypatia, celebrating their lives and the work of important women mathematicians. Pitter Pattern, exposing beautiful and enchanting patterns in dance, rhythm, and shape. Harmonious Equations with Keith Devlin and world music group Zambra, highlighting the most important equations of mathematics. And Mosaic, about peace, culture, and conflict in the Middle East. Karl and Erik Stern have co-directed a dance company that has performed internationally for 30 years. And he and Stern are on the Kennedy Center teaching artist roster for their work integrating dance and math. He is emeritus math faculty at Anza College and lives in the Santa Cruz, California area. A little bit later in the presentation, Karl will be joined by Laurel Shastri, who teaches dance integrated with science and language arts, as well as dance technique, and was associate director of Ballet Tennessee for 17 years.
Thank you so much, Rhody and CoM. So what I'm going to share with you today are kinesthetic puzzles that have some connection to dance in the arts. And I'm going to try to mostly share things that don't take a lot of movement that you can do while seated, but in some cases you might want to stand and move. And so you may be used to, in the recreational mathematical world, puzzles in which you're asked or challenged to try to do something that you didn't know was possible. But a kinesthetic puzzle, I think, a mathematical kinesthetic puzzle, has some of those same qualities, but there are also challenges as to how physically to do something, why physically something occurs, but also what do you have to figure out in order to make something work. So hopefully there'll be some elements of both kinds of challenges. And anyway, so what I want to start with is something that I learned from John Conway at a conference. He was always doing fun things. So what I'm going to share with you is a way of saying hello based on something that I learned from Conway. And now in the day when we don't shake hands. So what I want you to do is hold your right hand so that your palm is facing you. And the puzzle is, how can we turn the hand around and wave hello without twisting at the elbow? And so it goes like this. Your hand is facing you, but you want it to face away from you. And so what we're going to do is rotate the right arm, so down to the left, and now rotate it again to the front, and now rotate it up. And notice that it's now turned 90 degrees to my left, your left. And so let's do those three operations again. Rotate down to your left, out in front of you, and straight up. And now you can wave hello. And so there are these questions as to why that works. And interestingly, there are also connections to how, say, dancers or athletes move their arms. So, for example, in dance, you might have what's called second position. If a dancer moves her or his arms from second to what's called first position, and then up to fifth position, and then back, the arm has rotated 90 degrees. So here I go forward, up, 3 90-degree angles, all perpendicular to each other, and dancers or athletes moving their arms, or anybody moving their arm when they reach for the butter at the table, learns that you have to add a rotation of the arm so my palm faces forward. So there are these nice connections to how we move our limbs in space with this thing. But there's also this puzzle as to why is it that three of these perpendicular rotations rotate the hand 90 degrees? And I want to give you another bit of a puzzle. So there are a lot of ways to understand that, but let's look at this. This Mickey Mouse doll can do three kinds. I'm going to allow it to do three kinds of rotations. It can do a half somersault. There's a half somersault forward and a half somersault back to where it started. Or it can do a half cartwheel, and there's another half cartwheel. Or it can do a half spin, and there's another half spin. Now, I want you to model this with your hand. So a half somersault would look like that, and you can unsomersault it. A half cartwheel like this, you can uncartwheel it, or a half spin like that, and you can do the reverse, get it back to where it started. And the question I'm going to ask you is the following. There's the doll, and there's the half somersault, and the half cartwheel, and the half spin. And what is the result of a half somersault followed by a half cartwheel followed by a half spin? So model this with your hand. Half somersault, then a half cartwheel, then a half spin. Will the doll end up with its head up or down? Will it end up with its head facing away from you or facing towards you? Or with your hand, will your hand end up with a hand up or down, facing away from you or toward you? So half somersault, then half cartwheel, then half spin. So here's the half somersault, and here's the half cartwheel, and here's the half spin. So Mickey ends up back where Mickey started. And so there are three halves that in a sense make a whole, get you back to where you started. And again, these are rotations in one case of the hand. And there's something puzzling about it. And the question is, why does it work? But we can ask another question, which is, what if we did them in a different order? So we could start with the somersault or the cartwheel or the spin. In each case, we have two more choices. For example, after the half somersault, we could do the half spin and then the half cartwheel. And then finally, we have six possible ways of doing it. And is it the case, and you can try this with the palm of your hand, that no matter which order we put those in, Mickey ends up starting where Mickey started, or your palm ends up starting where your palm started. So in other words, if you do the spin, then the cartwheel, then the somersault, you start the spin, the cartwheel, and the somersault. Mickey starts where Mickey ends where Mickey started. And so now the puzzle is, can you explain that? Are they all the same? And it turns out that yes, all six of those start and end with Mickey in the same position. So why is it that these three halves always make a whole? I'll let you think about that for a few seconds. And it's again, a problem about rotations. Again, there are connections to the field of dance. So if I start with my arm in what's sometimes called low fifth position and move it to high fifth position by rotating forward and then rotate down to the side, notice that I've added a 180-degree twist, and I have to untwist to get back to where I started. So here's a rotation about this side-to-side axis, and here's a rotation around the front to back axis, and now there's an extra rotation about the vertical axis. Three rotations around three mutually perpendicular axes. Whereas if I go forward and then down, it doesn't do anything. And so I'll tell you what, when I give this puzzle to students, one thing they come up with is the following. Well, when you do a half, when Mickey does a half somersault, both the facing and the up or downness of the head switch. So Mickey's head is up and now it's down. And if you do the next half somersault, again, the up downness switches. But also now Mickey is facing front, and with the half somersault, now Mickey is facing back. So a half somersault switches facing and up or down, whereas just a spin only switches facing, and a cartwheel only switches up or down. So if you put those three together, they're going to cancel each other out. You'll have one that reverses facing, one that reverses up or down, and one that reverses both. And so that can also be used to describe what's happening with the arm. But I also like to play around with looking at this, say, in terms of my favorite Rubiks Cube, the 1 by 1 by 1 Rubiks Cube. Maybe it's my favorite because it's easy to manipulate, or easier. So I have the blue face facing you and the yellow up top. And if I do that rotation we did with our arm, 90 degrees to the left, and then one more to the right, what kind of a rotation does it take to get back to where I started? Well, it turns out that I can rotate around this long diagonal axis of the cube, and that gets me back to where I started. So somehow this 90-degree rotation followed by this 90-degree rotation is what seems to be a 1/3 rotation. And if I face the point of the cube towards you, you can see that that now, let me get this, there we go. The yellow is I think facing the camera, and 1/3 gets me here. White is up, 1/3 blue, and 1/3 of a turn yellow again. So somehow there's a third of a turn that is coincident with these two right angle turns. So again, there's a bit of a puzzle about what's going on and why. And what we're working with here are rotations around, again, the front to back axis, the left to right axis, and the up and down axis. I like to think of this as the x-axis with my right arm facing forward, the y-axis here, and this up-down z-axis. And so we're doing rotations of 90 degrees or 180 degrees around these three axes. And you see these kinds of questions arise in dance all the time because we're all moving our limbs, but in sports as well. So if somebody has a basketball and they're trying to keep it away from an opponent, they're often doing, say, a rotation around one axis and then another, and then another, not exactly around those axes, but intuitively when we dance or when we do sports activities, or as I said, when you move your arm at the dinner table, we know that we have to make adjustments. In fact, people who work with robotics know that if they have the robot do these rotations of the arm over and over again, if they're not careful and don't adjust the arm might break off. So you have to make adjustments of the arm, and we all seem to know this, but there are interesting mathematical questions about why it works in certain ways. So I want to go on to something else that you can do along with me, and that is we're talking about rotations, and so I want to think about arm or hand circles. So this you can do just sitting down. How many ways are there to rotate the hands together? both hands. So we can rotate, I'm rotating both of them together in a clockwise fashion. So try this with me. And then reverse that. But we can also have them go in opposite directions. And you can reverse that. So there are 4 ways to rotate the hands around this. I guess these are my x-axes, this front to back axis. But there are actually more ways. For example, if they're going in the same direction, we can have them out of phase with each other. Or we can reverse that. So I hope you're trying this. So there are 2 ways. We're up to 6. Now, what if they're going in opposite directions? Well, they can still go out of phase in one way or the other way. So now we're up to 8 ways that we can rotate the arms in keeping them in a plane. And if you want to stand up, you might try this with your whole arms, both together in one direction or in opposite directions, and you can reverse that. But what about out of phase? Or we can reverse that, or we can go, and those were in the same direction, or we can go in opposite directions, out of phase, or reverse that. So we can also do these arm circles using the whole arm. But what about not just the front to back axis, but the side to side axis? So here's a rotation around the side and of the other arm. We can do both arms together, or like in butterfly and swimming, or you can alternate like in swimming, say freestyle and so on. So there are lots of ways to do this. But now here's a bit of a puzzle, the next puzzle. We did these hand circles in a flat plane, both circling around the front to back axis. What if we circled them around the right to left axis? So we can do them both together or both in the opposite direction. And it's probably easy for you to rotate them so they're out of phase in either direction. So there are 4 ways, but what about going in opposite directions? Can you get one hand to circle this way and the other to circle that way at the same time? So try that. And now I'm going to show you a couple of tricks that will allow you to make that work. One is, let's rotate our hands in front in the same direction and very slowly turn them so they're facing each other, and then go back. They're going the same way, but turn them so they're facing each other, and then it should be easy. Now, here's another way to try this. Just kind of swing the hands back and forth in opposite directions and let the swing get bigger and bigger until it goes over the top. Well, what about if they're out of phase and then you slowly have them face each other? Interestingly, when they are in phase and you point them towards each other, they pass at the top and the bottom, the top and the bottom. When they're out of phase and you turn them towards each other, they pass close to you and then away from you, close to you and then away from you. And that's, so they can either pass here and here or up and down, interestingly. Anyway, those are ways of playing with that, but you can also play with these ideas using whole arm swings. Is there a way for me to circle my right arm in one direction and my left arm in the other direction? Well, there is, but it's a little tricky. or we can go back in this direction. Now, there's one more complication to this, and it goes like this. If I hold my palm facing up and do a complete rotation with the palm always going in the direction of motion, it's going to end up twisted a complete turn. So I'll try with my left arm. Oh, it also ends up with a complete twist in it. And if I rotate around this axis, it also ends up with a complete twist in it. Or if I rotate around the vertical axis, it also ends up with a complete twist. And it actually takes not one, but two complete rotations, one in front and one in back, to undo the twist. So here's one, it's twisted, and here's one in back, and now it's untwisted. And there's a wonderful way of explaining these kinds of things mathematically that we learned to play with using a piece of paper. So many years ago, we started making dances where we manipulated a piece of paper and discovered, oh, if I do one complete rotation in front, I better do the one in back if I don't want to drop the paper. And what are the Quaternions? Well, they kind of work like this. You have three variables, you could say I, J, and K. I represents a rotation of 180 degrees around the x-axis, so 180, and I squared, that's going to be like a -1. But also around the side-to-side axis, that's going to be like a -1, or I could just rotate it like this, and there's my -1. Or I could rotate it around the top. That's around the side-to-side axis is going to be called J, and J squared is also gets me in the same position as I squared. So if I rotate around the side-to-side axis, it ends up in exactly the same place as if I rotate around this axis. And if I rotate around the vertical axis, it's in exactly the same place. I squared, J squared. So this is K. K squared is this, and that's the same as J squared, and that's the same as I squared, and they all get called -1. Okay, well then, if this is -1, then -1 squared would get me back to 1, to the original position. So there's a connection to what are called the Quaternions, which is one of several ways, nice ways of trying to mathematize what happens when we combine rotations in three-dimensional space, especially rotations of our limbs. And as I said, dancers are always doing these things. I just want to show you one other aspect of this. Here's a belt. If I twist the belt once, complete turn, the belt buckle is going around another complete turn. So start here, and the buckle goes around once and around twice. It's actually keeping the buckle going the same direction, equivalent to no rotation. So here's one rotation, and here's another rotation. And if I pass the buckle under, but keeping it in the same direction, it's not really twisted. And you can also think of this as doing one rotation this way and one rotation in back, and it's not twisted. So it turns out that an odd number of rotations are equivalent to each other, and an even number are equivalent to no rotations. Kind of a curious fact. And I want to give you some other little puzzles. So one is just to try to explain some of the sequences of arm rotations by looking at rotations of 1 by 1 Rubiks Cube, or looking at how we rotate a doll. So interestingly, you can do some complicated mathematics with just rotating a doll. But you could also look for some interesting or unusual ways to make circles or swings in the air with different parts of the body. For example, maybe just elbows, or maybe legs, or the following. Here's now, and you might want to create a series of movements and play around with them. Okay, but here are some body rules. Try to make circles with one hand and one foot. So let me move out of this. And we're also going to try circling index fingers in a way. So can you rotate a hand and foot in the same direction or opposite directions? Now we tried this thing where the hand goes in one direction and the foot goes in the other direction. I don't know about you, but I find this almost impossible. Can you practice and get them going in one direction and one in the other? Now try it. Now that was with same hand and right foot. Try it with right hand and left foot. Interestingly, I find that very easy to do. And so I have a feeling this says something about the connection between our brain and different parts of our body. The right hand and right foot are connected supposedly to the left brain for most people. And since the left foot is connected to my right brain and the right hand to my left brain, perhaps that enables me to rotate them in opposite directions more easily than same hand and same foot. And here's another mathematical kinesthetic puzzle, and it goes like this. We're going to rotate our fingers pointing towards each other really, really fast, and you might find if you start them together, they start moving out of phase. So the faster you go, faster I go, the faster they seem to get out of phase. And here's another little body puzzle. When I rotate my fingers really fast in the same direction but pointing away from me, pretty quickly they get out of phase. Why is this happening? And perhaps someone can figure that out. I have no idea, or who knows? It seems to happen for many people. Okay, let's see what else we can do. So we've been doing a bunch of things here with hands and fingers and so on. And what I'd like to do is show you some more puzzling things with fingers. So here's a picture of Scott Kim. Now, Scott started working with our dance company about 25 years ago, and he brought to us something he called finger geometry. And he was showing us ways of making things like a tetrahedron or a cube with the fingers. And I'll get to Dave in a minute, but let's show you a way of making a tetrahedron with the fingers. So unfortunately, this is going to take two people. So hopefully, perhaps you have someone in your family or close enough to you that you can be unmasked, as my wife Laurel and I can do. And what Scott first showed us was, well, here's a way to make the tetrahedron. We place our thumbs together and point our fingers away so the fingertips are kind of a square. And we face each other, and one of us rotates 90 degrees, and there's a really nice tetrahedron. And then he said, well, you can also make, if we rotate like this, turn one and put the thumb and finger together. Well, here's a way to do it. You point these and point these at me. So they're facing each other and we interlock. And there's a pretty nice cube. So we can go back and forth between that and the tetrahedron. And when Scott started showing these things to us, we started making dances with the hands. I'll show you some clips of some of those things. But then I let me show you one other person here. Momath doing something, and Dave Masanaga was there. He lives in Hawaii, and he said, well, let me show you another way of making the tetrahedron. So show you this other way. It goes like this, and something that Scott said generated his first finger tetrahedron was he was at a talk with Buckminster Fuller was doing, and he realized that you could take a triangle like this and take the edges slightly apart and take two copies that are mirror images and put them together like so. And so Dave said, well, we can also make a tetrahedron by putting our thumbs together and index fingers together to make a triangle and slightly rotating them. So Laurel and my hands are mirror images of each other, and we can, let's bring it close to the camera, we can make a nice little tetrahedron this way. So there it is. And notice the tetrahedron has 6 edges. My index fingers are 2 edges. My thumbs together make a third, and Laurel has three of these edges as well. So we have a total of 6 edges, and those actually go together in 2 different ways. Well, there are many, many ways to make, say, a tetrahedron with several fingers. So here's another way. I can use these 3 fingers and these 2, and now I need one more edge, and Laurel will add that one edge, or she can have 2 of her fingers, and I can add these 3 and then one more of mine. And so I challenge you to play around with this and find as many ways as you can to make a tetrahedron. Laurel the other day said, well, what about with the legs? And she made a tetrahedron like this. I don't know if you can see it, but I've got 1, 2, 3, 4, 5, 6 edges with the body. So playing around with these shapes, kind of fun. And let me show you a few images. So here are some students in Puerto Rico making 4 students making a cube with their fingers. And here's some people at one of the Bridges conferences making a cube with our bodies, and actually very similar to something I did with the group called Children's Dance Foundation in Birmingham prior to that. And here's some images for making all the Platonic solids or polyhedra with 6 dancers. And this got us thinking about, well, are there ways to, say, use sticks, PVC pipe, to make in dances? And here's one more. Let me see if I can make this work here. I call this the squishahedron. So it's got a puzzle, but it's also got something a little. This is called a tetrahedron. And this is a puzzle with the tetrahedron. Can you fold this shape to form the shape of the tetrahedron? I'll come back to that in a minute, but first I want to show you something called the squishahedron. Now, what is the squishahedron?
If you like those tetrahedra, what about this? A tiny tetrahedron with 4 fingers. If I open it, you can see the point, but if I put the piece of gum in it and squish it between the 4 fingers, you actually see it's a tetrahedron. And what if you put 3 fingers together? If I open the door, you see it is actually a cube in there. If I put the piece of gum in there and squish it down, it actually is a little bitty cube.
Here's that tetrahedron, and notice it has 4 points or vertices where 3 PVC pipes or edges come together at each vertex. And this shape has these vertices here. These bottom vertices have 3 edges already, the top ones only have 2, so somehow I've got to add an edge to each one of these. Now, if I had held it more like this, it might have been easier to see that we can add an edge to this vertex this way and one to this vertex to form the tetrahedron. That's a puzzle we often give the audiences when we perform. Here is a set of images from a dance where we use these PVC pipes to make various shapes. There's an octahedron, and the same one's used to make a cube, and kind of a 4-pointed star. But we also do imagery like rowing or flying that have nothing to do with mathematical polyhedra. And here are some other images for using shapes, ropes and arms and bungee cords in the bottom left and PVC pipe, and also with string. And here's, hopefully you can see this. And these roll together very briefly to form a tetrahedron. But the goal of the dance is not just to make mathematical shapes, is to have fun and be playful with the shaping process. And here's one more, I think, slightly different. Yeah, with the same PVC pipe. And the video is not in slow motion. We're actually just moving slowly there. Here's some more images. This is using paper straws held together by pipe cleaners and a drop of super glue. And the goal is, or the puzzle is, to figure out which ones can be folded to make various shapes. Well, speaking of making shapes, I have maybe time for one more puzzle, and goes like this. I was talking to Scott a number of years ago, and he said, well, you can do Itsy Bitsy spider with your fingers, with your thumb and forefinger, like so, where you rotate and move a little bit higher. And he said, well, he had been playing around with Itsy Tritsy spider. In other words, if bit is for 2 and Tritsy would be for 3, what can you do with 3 fingers? And so I started recently looking at this, and I'm going to use the thumb, the index finger, and the middle finger of each hand. So with Itsy Bitsy spider, we usually start by pointing the index finger at a thumb and then rotating and moving higher and higher. And so you start with one hand facing away from you and one hand facing towards you, and you can't put thumb to thumb because when you twist them like so, the index fingers will either be on top, but one on top, one on bottom, or if you put the index fingers together, when you twist them, it doesn't work if you want to always have one hand facing away and one hand facing towards you. So you have to start with not index finger to index finger or thumb to thumb, but index finger to thumb and vice versa. And then you can do Itsy Bitsy spider. Well, so let's look again at Itsy Tritsy spider. So there is my hand, my left hand is facing away from me, my right hand is facing towards me, and I'm using thumb, index finger, and middle finger. And if, I don't know if this is the way, I can make a little chart where the left-hand fingers are 1, 2, and 3 are shown in black, and the right-hand fingers are shown in blue. And so there I put the words, 1 is thumb, 2 is index finger, 3 is middle finger. And I'm not going to have thumb to thumb because, again, that doesn't work for Itsy Bitsy spider or Itsy Tritsy spider. And I'm not going to have middle finger to middle finger because that also is not going to work if I always want one hand facing away and one hand facing towards me. And I'm going to start with 3 to 2. In other words, my left middle finger to my right index finger. And the question is, can I get to all of the other 7 connections between the fingers without repeating any? Well, if I now twist, I can now do, there it is, 2 to 3. So I start with left middle to right index. I twist, and now I can do left index to right middle finger. And on the chart, that's 3, 2. So 3 left, 2 right. And on the graph, there's that point 3, 2. Now from 3, 2, where can you go? I could go to 1, 3. So you see the left thumb and the right middle finger could be joined like so. So there's 3, 2. It could go to 1, 3, and there's the little arrow. And because the 1 and 2 are less than 3 on the left hand, and the 3 is greater than the 2 on the right hand, that red arrow is going upwards to the left. Well, I could also join 2 to 3, the left 2, the left middle index finger to the right middle finger, and then that would be that arrow also going upwards to the left. I'm going to choose the left index finger to the right middle finger, and I'm going to go over this again for you. So hang in there. What can we do next? Well, when you swivel the hands, so now the left hand is facing away and the right hand is facing towards you, 2 and 3 are connected. Left index and right middle finger. What else could we do? Well, we could go 3 to 2, but we just did that. We don't want to repeat that. So I'm going to do left middle finger to right thumb. And notice the 3 in the left hand is bigger than the 2. And the 1 on the right hand, the thumb, is smaller than the 3. And so that's going to create an arrow going downwards to the left. Now, when we swivel the hands, we're always going to alternate moving on the chart upwards to the left and then downwards to the right. And we can actually continue in this fashion. I can go to left thumb to right index, and that's an upward red arrow to the left. And then I can go down to left index and right thumb, and that's a green arrow downwards to the right, and continuing until I get to all of the ways of joining those fingers that work with Itsy Tritsy Spider. But the real question is, can we physically do this? We're going to start with our left hand facing away from us. We're going to use just the thumb, index finger, and middle finger of each hand. The right hand is facing towards you, and you join your left middle finger to your right index finger. And then we twist both hands, and now we do left index to right middle and twist them again, and we do left middle finger to right thumb, and now we do a bunch of thumbs. We twist again, and we do left thumb to right index, twist again, we do left index to right thumb, twist one more time, and this time we do left thumb to right middle, and finally twist one more time, and you end up with the 2 index fingers pointing at each other, and we've done all 7 possible connections. So let me show you what might come next. Is Itsy Quartzy Spider, where you have fingers 1, 2, 3, and 4, and no thumbs. And there's that 3 joined to 2. And is it possible to do all possible connections? We won't do 1-to-1, pinky to index finger, or vice versa. But it turns out that we can alternate. And here's one possible sequence. When you get to all of them, that creates what's called a Hamiltonian cycle of all of those possible ways. There are 14 of them of joining those fingers. an Itsy Quartzy spider. And then you might ask, well, what about Itsy Quincy spider? Now, if somebody can do that and make a video, please send it to me. I would be intrigued to see what, how quickly you're able to. And so just to go back, you might play around with this. And once you've got it, so I'm going to do left, middle to right index finger. Once you've got it quickly, you might challenge other people, see if they can do. And then I twist, and then I twist again, and again, and again. And finally, I get to index finger to index finger. And those were all 7. And it took me a while to practice that without looking at the chart. Okay, so let's see if we have anything else. Yes. So this is a way of pairing fingers, but is there a way of pairing dancers? So how might 12 dancers dance with each other dancer? So you have 12, let's say you have 12 dancers on stage, and you want to have 6 duets going at one time, but you want each dancer to do a duet with, at the same time, with all 11 other dancers. Well, is there a way to do this so that you have 6 duets going all the time, and every dancer dances with every other dancer once? And can you do it with 11 rounds, with 11, having 11 sets of 6 duets? And there is a way to do this, though I've never had a group of dancers do it. It's called turning. And this graph that I showed you with, it's called the complete graph on 12 vertices. And the lines between the two, any 2 pair of dancers, indicate that they're doing a duet together. So there's a line from 11 to 3, for example, and that line segment indicates that you want 11 and 3 to do a duet together. Well, there's a way of taking that, all of those things apart and arranging them like so. 1 through 11 are in a circle, and 12 is out on the outside and rotating. So 12 on the left there, 12 and 1 do a duet together, 2 and 11, 10 and 3, 4 and 9, 5 and 8, 6 and 7. And I first started thinking about this. And then 12 rotates, and 12 dances with 2, and everybody pairs up like the next picture. And then 12 rotates again, and so on until 12 is doing a duet with 11. And I first started thinking about this when Laurel was working with a group of teaching artists, and they wanted to do what's called pair sharing. So they had 12 people in their group, and they wanted everybody to spend a minute talking to everybody else. Was there a way to do this in 11 rounds so that everybody pair shared for a minute with everybody else? Now, nowadays, we do this kind of thing on Zoom, but I've noticed that the people who make the Zoom software haven't really made a nice way for us to do these, create these kinds of arrangements by hand. Now, this turning method is sources from a book called Pearls in Graph Theory by Gerhard Ringel and Nora Hartsfield. And Gerhard was actually my thesis advisor. Nora was a fellow graduate student. And here's a way of doing this conveniently with people, either dancers moving around in a cycle, and one dancer, number 12, just kind of sitting out to the side. So again, 12 starts with a duet with 1 and the other dancers pair. And if you're doing pair sharing, you could have a table down the middle there, and everybody talks to the person across the table. And this also works for an odd number of dancers or an odd number of pair sharing, except because there's an odd number, one person is left out. And now this has some applications, this kind of thinking. Here's a kidney donation puzzle that Scott Kim made a number of years ago. And each circle represents a pair of people, one of whom, say they might be close family members, one of whom needs a kidney, and the other of whom is willing to donate a kidney, but for some reason, maybe by blood type or incompatible blood type, the family member cannot donate the kidney to the other family member who needs one, but could donate to someone else. So on the left, you have all the possible pairings that work. Okay, so anyway, this has applications in the medical field. So you can find us at danceandmath@gmail.com, that email, or if you just Google Dance and Math and my name, you'll find us, and my email is there. And we do have a group that meets to discuss online, to discuss dance and math once a month. The next one is Sunday, October 7th, at the same time in the morning. So yeah, look for us under mathdance.org or Google Math and Dance, and you'll pretty quickly find us.
And Karl, I'll mention to you that there were a number of interesting questions that came up in the chat. Some people had some conjectures about why did things get out of pace. A few people had connections to other things. So
well, let's look at those.
You want to take a look at that if you'd
what
like.
was the out of pace question? Oh, was that with the quick finger thing?
Yeah, somebody suggested it was the dominant hand, maybe. Somebody suggested that it was conservation of momentum. Like you said, I don't know why this is. And somebody just posted a question right now. I like the Quaternion algebra interpretation of the movements of the hand-arm rotation. I think of it as the holonomy around the geodesic triangle on S2. Either way, have you developed the intuition to do more general Quaternion multiplication / holonomy computations with your arms?
Not really, just pretty well, some. And I have a paper in the Bridges Math Art conference you can find online that deals somewhat with this. But what I was mostly interested in is this kind of swirling motion that you see in dance. And it's usually done quite beautifully. You have kind of double circles of the arms. I don't know if I can be seen doing that. And so I was curious if there was a way to mathematically explain what's going on. And yeah, there is, because I think the Quaternions are the best way to explain that. And this double rotation is best explained by looking at SU2, or it's what's called the double cover of the set of rotations in 3 dimensions. So this Quaternion algebra is kind of double what, in some sense, how we usually think of rotations in 3-dimensional space. And that's why we get into this doubling circle kind of thing. So I think it would be a nice puzzle to work out ways of making your arms be compute various Quaternion computations or rotational computations. Can we make our arms into a computer besides just using them in fun ways? Now, as a dancer and choreographer, I tend to be more interested in doing beautiful patterns with the arms. And with dancers I work with, I'm often challenging them to do these kind of swirling motions. And I do try and pay attention to this double circle property of them. But I think the answer is no, but why don't you develop this? In other words, make your arms into a Quaternion computer and see what you can come up with. But also, would what you come up with be fun to watch as dance? What would happen if you set it to music? What kinds of creative things can you do besides just using your body to do computations? If this makes sense, I try to think of the art form as just as important, or maybe even more important, than using it to illustrate mathematics. We can do that, and the two can feed off of each other. The illustration of the mathematics can help us understand, say, what we find beautiful about swirling movements.
Okay, so I think that's all the questions. Karl, that was so wonderful. I'm going to be playing with my hands all day long. Thank you so much. Okay, bye, Karl.
Bye.
Bye, everybody. Thank you for coming.